This video will be about moisture transfer, how moisture is transferred from one place to another. And we'll learn to understand the concept of capillary suction, diffusion, convection, gravity and wind pressure. Capillary suction, we have mentioned this in a previous video, due to the fine pores in building materials in contact with water or in contact with coarser materials, moisture can be transferred by capillary action. So this has to be dealt with, and you have to introduce capillary breaker, for instance, between wet concrete and wood in a construction. Vapor diffusion. We illustrate that with, let's say this is a piece of paper in air on the left hand side, and we have equal amount of water vapor molecules bouncing around in the air on both sides. And the piece of paper will be hit by molecules equal amount from left to the right, so there will be no possible transport, that is through net transport in any direction. However, as illustrated in the right hand side picture, if we have more molecules on the bouncing around and hitting the piece of paper from the left hand side than from the right hand side, there might be a net transport from the left to the right. This is what we call a diffusion process. And if we have a small hole in this piece of paper, the molecules will not find it. They can't know where it is because they're just bouncing around and hit all the areas equally often. But of course, once we have a hit by a molecule in a hole, it would pass easier. The diffusion process is driven by differences in vapor concentration, or the difference in the humidity by volume. Analogous to thermal resistance, that's reduced heat flow. If we have a temperature difference, vapor resistance instead reduce the moisture flow by diffusion. And we have a vapor resistance for a layer, analogous to the thermal resistance. We denote it as capital Z and has the unit second per meter. And for layers with very high vapor resistance, we call them vapor diffusion barriers. And here are some values for Z, for the vapor resistance for different layers, and all are in a range of thousands. So like 40 millimeters glass fiber is 2000. The other range is 0.2 millimeter polyethylene foil is 4 million. So you have a great variety, and we have, like, the insulation material, gypsum, plaster are quite open. They have diffusion open, they have a small or low vapor resistance, while the roofing felt and polyethylene foil are very moisture tight with a high vapor resistance. Moisture convection. This is analogous to heat convection, where air is transferring heat. When we talk about moisture convection, instead the air is carrying water vapor, since the air contains water vapor and the air is moving with transfer water vapor from one place to another. And if we have an air pressure difference, like it's illustrated in the picture here, on the left hand side we might have a higher air pressure than on the right hand side. The air will find a hole. It can be a smart transfer process. This occurs in reality, for instance, when we have air or moisture convection up to a cold attic. We have then a positive air pressure inside because of the stack effect, because the warmer air inside. And for a small hole of 10 millimeter and a 2 Pascal air pressure difference, as much as 1 liter of water per month can be transported up to the cold attic and cause problems. So, in order to protect the building envelope from moisture diffusion and moisture convection, we're very often using vapor barrier that is both airtight and sufficiently moisture tight, diffusion tight. Airtight is very important in order to have energy efficient buildings and also moisture safe buildings. The layer, the vapor barrier, doesn't have to be totally moisture tight. As a rule of thumb, we say that the inner side of the construction, there should be diffusion tighter, at least five times diffusion tighter layer than on the outside. So in that way we restrict the amount of moisture coming into the building envelope from the inside, since we have a higher vapor concentration on the inside. And once we are outside or out in the building envelope, there should be an easier way, less resistance for moisture diffusion, so it can dry out outwards. Gravity and wind pressure is also important. On the left-hand side we see the example with driving rain. So we have driving rain on a facade, and we have what we call a runoff. A film of water is running down the facade. And this, if we have cracks and holes, this water can be pressed in by the wind pressure, and it can go deeper into the construction in the building envelope. And this has to be handled by drainage, or at least having construction that can withstand this type of moisture transfer. The right-hand side picture, we have an example with a flat roof, and it must be during the spring when snow and ice is thawing on the roof, and there could be small puddles with water where you have a build-up of water pressure. And if you have water pressure, it can press down into holes in the building envelope, and you really need to have watertight layers on the roof in this case to avoid it. Summary. Moisture can be transferred by capillary suction, diffusion, convection, gravity and wind pressure. Diffusion of moisture flows from spaces with high humidity by volume to spaces with low. The amount of moisture that is transferred by diffusion depends on the exposed area and the diffusion resistance. Moisture convection is caused by airflows that exist due to air pressure difference across the building envelope. High airflow rate and high indoor humidity by volume increases the moisture transfer by convection. A vapor barrier can eliminate both moisture diffusion and convection.